Yeah, thank you, Bernhard, for the introduction, and thanks to the organizer of the seminar for giving me the opportunity to report on recent work, to join with Simon Brendle, Bernhard Hanke, and Yipeng Wang, who will give the second talk this afternoon. So my talk will consist of two parts. The first one will deal with certain index theoretical considerations, and in the second part, they will be applied to scalar curvature problems. So let's start with the index theoretical part. All right, so here's the setup. So we consider a compact Riemannian spin manifold with boundary M, and we are given two metrics on this manifold, G and G naught, and we have the corresponding spinor bundles, which I denote by S and S naught, and the corresponding Clifford multiplications, which I denote by gamma and gamma naught, correspondingly. We look at the Dirac operator for the metric G, but we twist the spinor bundle for G with the spinor bundle of G0, or rather the dual of the spinor bundle of G0. So the sections on which this operator will act are sections of S tensor S0 star. And now the two more pieces of notation. Nu will denote the outward pointing unit normal vector field with respect to the metric G. And N will be another smooth vector field on M along the boundary, this time of unit length with G naught. So it could be the outward pointing unit normal field with respect to G naught, but it doesn't have to be necessarily. So it's just, for the moment, it's just some unit vector field with respect to G naught. And once we have these data, we can define a chirality operator. So what we do is we take this unit vector field nu, so along the boundary, we take the unit vector field nu, which is a unit vector field, and Clifford multiply with it. And so that's what acts on the S part of the twisted tensor bundle. And similarly, the vector field N is given Clifford multiplied with respect to the metric G naught. This way, we get an operator, an endomorphism field on the bundle S tensor S naught star along the boundary. This minus sign is just for convention. And now, since the Clifford multiplication of a unit field squares to -1, so both square to -1, so the whole chirality operator squares to +1. And since Clifford multiplication with vectors is skew symmetric, the tensor product is symmetric. So we get a self-adjoint involution on our bundle. And then also we have the corresponding subbundles of eigenspaces, which one can show actually turn out to be of equal dimension. Okay, so that's the setup. And let me give the Dirac operator boundary conditions. So I will distinguish between the odd and the even dimensional case because they are slightly different. So let me start with the odd dimensional case. So I just look at these sections of M tensor S of S tensor S0 star, and I give them the boundary condition that the chirality operator. So I have two boundary conditions, one for plus and one for minus, and I just require that along the boundary my spinor field is in one of these two sub bundles of eigenspace plus or -1. We will use both conditions. And they map to S tensor S0. So, and then this is an elliptic boundary condition. And so we obtain a Fredholm operator. And the first theorem tells me what the indexes will be. If we assume that the vector field N be homotopic to nu through non-vanishing vector fields. So for example, if N is the outer unit normal vector field with respect to G naught, then we can compute the index of D plus and of D minus, and we get the Euler number of the manifold M. And so note there's an index as a minus sign in the index here, so divided by a minus sign. So that is the statement in odd dimensions. And in even, and also note, M is a compact manifold, but with boundaries. So in general, the Euler number of the manifold will be non-trivial, right? Even though it's odd dimensional. And in even dimensions, we again use the same boundary conditions. So involution of psi along the boundary is equal to plus or minus psi along the boundary, but we restrict ourselves to a certain subbundle. In even dimensions, both the spinor bundle S and the spinor bundle S0 decompose into these chirality subbundles. And I look at the subbundle S plus, tensor S plus, and S minus, tensor S minus. So I look at this subbundle of half the rank and restrict my operator to that. And this maps then to S minus, tensor S plus, and S plus, tensor S minus. So the twist bundle is, of course, unchanged, but the Dirac operator changes the chirality of the spinor bundle with respect to the metric with respect to which we take the Dirac operator. So we have this, this restriction of the operator, otherwise we would not get a non-trivial index. And in this situation, we can again compute the index under the assumption that n is homotopic to nu through non-vanishing vector fields. And again, we get the result as the Euler number. The only difference to the previous situation is now that there's no sign in this case, right? So both the S plus and the D plus operator and the D minus operator both give the same index, which is the Euler number. And so that is a statement that will be used later in the second talk by Yipeng Wang. For the proof, just let me say the following, namely, first of all, by deformation invariance of the index, we can deform the metric G to G naught and the vector field N to nu, so that we can, without loss of generality, assume that G equals G naught and N equals nu in the first place. And if that's the case, then if we take the product of the spinor bundle with the dual spinor bundle for the same metric, then there's a canonical vector bundle isomorphism to the form bundle, at least if n is even. If n is odd, then this second part is bigger than the tensor product of the bundles, then we have to restrict to a certain subbundle of this form bundle. And this then allows us to translate everything to differential forms. So we translate the Dirac operator to differential forms, and we translate the boundary conditions to differential forms. And it turns out the boundary conditions get translated to what's called the absolute and relative boundary conditions for forms. It's a mixture of both, actually, depending on the degree. But then you can apply Hodge theory for these, and then you will get the Euler number. Because Hodge theory will relate the kernels of these operators, these harmonic forms under absolute and relative boundary conditions to the Ram cohomology for absolute and the relative de Ram cohomology relative to the boundary, and then you can figure out then you can compute the index, and it turns out to be the Euler number. So that's this kind of a statement is implicit in the literature in various places. It comes up, for example, in work by John Lott and others. But I think it's good to state it in this way, so that this will turn out to be useful later. So that is the first index theoretical remark I want to make. And now, more seriously, is the second index theorem, which I'd like to call the holographic index theorem. Holographic because we treat, again, manifolds with boundary, but this time we will relate the index of the manifold with a certain boundary condition to an index on the boundary. So something in the interior is related to something on the boundary, and that's why we like to call it the holographic index theorem. So what's the setup? Again, we look at a compact Riemannian manifold with boundary M. Again, now we have just one metric. We look at its outward unit normal vector field nu, and then we have any Dirac type operator acting on a vector bundle over this manifold M. So Dirac type is like the largest class of Dirac operators that you can consider. It need not necessarily be a twisted spinorial Dirac operator. The only condition is really that the principal symbol of this operator satisfies the Clifford relations. So you can add any potential to the operator, and also it's not required that the principal symbol is parallel, as you do when you consider generalized Dirac operators in the sense of Gromov and Larsen. So this is like the biggest class of operators that deserve the name Dirac. And then associated to this operator on the manifold M, we have an adapted operator, or we assume we have an adapted operator on the boundary. And this adapted just means that there's a compatibility condition between the principal symbols, which I have here. So essentially the principal symbols coincide. except that the principal symbol of along the boundary, the principal symbol is composed with the principal symbol, or rather its inverse applied to the unit normal vector field. And from this, it follows directly that this operator on the boundary is also of Dirac type. Yeah, this also satisfies automatically the Clifford relations. Furthermore, I assume that my bundle on which the operator acts, when I restrict it to the boundary, decomposes into two subbundles, and that my boundary operator interchanges them. That's an assumption that I make. And and the space that I'm now considering is the space of smooth sections up to the boundary, which satisfy, again, the condition that along the boundary, I'm either always in S plus or always in S minus. So similar to the previous case. That's the situation now. And now we observe, furthermore, we assume that the operators are formally self-adjoint, that the principal symbol, so think of it as Clifford multiplication with the normal vector field, preserves these two subbundles, and it anti-commutes with the boundary of Dirac boundary operator. So these are the assumptions. All right, here's the theorem. I can look at the index of the operator on M, subject, let's say, to the plus boundary conditions. And then I can relate this directly to 1/2 the index of the boundary operator on the boundary, which is acting actually on a closed manifold, which maps S plus to S minus. And similarly, you can replace, interchange the pluses and minuses in the whole formula, and they get the same thing up to a sign. So that's the holographic index theorem. And the nice thing about this is that the right-hand side, so this index of the boundary operator, this is something taking place on a closed manifold, compact without boundary. And so it can be computed using the usual Atiyah-Singer index formula in applications. And that's what we will do later when we apply the whole thing to the scalar curvature problems. All right, now here's a short sketch of the proof. Here again, you have the formula. Index on M is related to the index of the boundary. And how do you prove that? And so what you do is this. You look at the space of all sections along the boundary. This is Sobolev space of H1/2 regularity, not so important. It's a technical thing. And you can decompose this space. You can look at V plus, which stands for the sum of all eigenspaces to positive eigenvalues of the boundary Dirac operator. And similarly, V minus stands for the sum of all eigenspaces for negative eigenvalues, and H is the kernel of the boundary Dirac operator, of this operator here. You have this decomposition, right, by self-adjointness. This is an L2 orthogonal decomposition, but I do it in H1/2. And this space H can be further decomposed because I can intersect this space with those harmonic sections which lie in S plus and those which lie in S minus. Remember, along the boundary, our bundle splits into S plus and S minus. And by the assumptions, then H is the direct sum of H plus and H minus. So I have this decomposition of the sections along the boundary. Okay, and now I can do a deformation argument. So the index that I want to compute actually, which is here on the left-hand side, so this can then be deformed by a deformation of boundary conditions. So I change these boundary conditions to the boundary conditions which you see here, which is V greater and plus H plus. So these are generalized Atiyah-Patodi-Singer boundary conditions. They are non-local boundary conditions, while the boundary conditions which I started were local boundary conditions. And some of you may remember that last year I gave a talk in this seminar where I described the general theory of elliptic boundary conditions. Of course, I'm not assuming that you remember all these technical things, but if you look at that, you can write down an explicit deformation between these two boundary conditions through elliptic boundary conditions. And then by deformation invariance of the index, the indices must be the same. The operator is not changed, but the boundary conditions are changed. Okay. And so then we now need to compute this index. Oops. We now need to compute this index, right? Okay. Good. So let's do that. So first of all, if I look at these Atiyah-Petodi-Singer boundary conditions called V+, so let's look at this first line here. And then I can take the adjoint boundary conditions, and they turn out to be V+, but I have to add the kernel. So, and then since these are the adjoint boundary conditions, I get the negative of the index. This gives me the first yellow line here, because the Atiyah-Petodi-Singer boundary conditions are almost self-adjoint except for the kernel. So if you pass to the adjoint, then you have to add the kernel. So this gives me this one line. And the other line is coming from a general statement that if you change a boundary condition by something finite dimensional, in this case h, then the index changes by just adding the dimension of this finite dimensional space. So this gives me the lower line. And if you combine the two, then you get what we have on the right side, namely that the index of Atiyah-Petodi-Singer is exactly -1/2 times the kernel of the space of the kernel, -1/2 the dimension of the kernel. Okay, good. And now we can do the computation. So what we want to compute is this index. That's what we want to know. That's what we are aiming for. And again, by this general formula that if you add a finite dimensional space, this is the index of Atiyah-Petodi-Singer plus the dimension of H plus. But for this first part, we have just obtained a formula up here, which we can put in. And then we get, so we have to subtract 1/2 the dimension of the full space H. So then 1/2 of H plus remains, and 1/2 of H minus has to be subtracted. And this gives me the 1/2 the index of the operator on the boundary. So that's basically the computation. And so the crucial thing is really to find this separation between these two different boundary conditions. Okay, so that's the holographic index theorem. And there are some special cases which are of interest and which I will also use in my talk later, namely these bundles S plus and S minus. For example, I can choose them as the eigenspaces of the involution I times exterior Clifford multiplication with nu. So this squares, nu squares to -1 and I, so the whole thing squares to +1. So that's an involution. I can take the eigenspaces. And if I then look at this formula, then actually the whole thing turns out to be 0. So this is a version of coordinates and invariance of the index. Of course, that's not good because we will use the index theorem in such a way that we produce a non-trivial index so that we can find solutions to certain boundary value problems. But nevertheless, at the moment, so that's what we find. And let me explain you why that is. Namely, why do we get 0 for this particular choice of involution? Well, without loss of generality, I can assume that M is connected because otherwise I just look at each connected component separately. And I can also assume that the boundary is non-empty because in the closed case, the thing is clear, right? In this case, you just have the index of a Dirac operator on a closed manifold without chirality decomposition, and that is 0. So we can assume that M is connected and has non-empty boundary. Okay, and now we need to show that the kernel of the operator under these boundary conditions is trivial, because the index will be given as the kernel of C plus minus the dimension of the kernel of C minus. So if I show that both kernels are actually 0, then certainly they're different, so the index is 0. So that's what we need to do. Okay, so let's assume we have something in the kernel of either satisfying the plus or minus boundary conditions. Then we can do the following computation. So I look at the integral ds times s minus s ds. So both terms are 0 because ds is 0. I assume that s lies in the kernel. So that gives me 0. On the other hand, by integration by parts, I can obtain a boundary contribution to this, which is given by this general Green's formula. And now the boundary condition pops in, which tells me that this is either plus s or minus s, or up to the factor of I. So what we get is up to some prefactor is the integral of s squared, and that is 0. So s is 0 along the boundary. So what we have then is a harmonic spinor on a manifold with boundary, which vanishes on the boundary. And if you have that, then it follows that this section actually vanishes on all of M by unique continuation. That's a particular property of Dirac type operators, which is not true for all elliptic first order operators, but for Dirac type operators, it's true that if something vanishes on a hypersurface and satisfies the equation, then it must vanish everywhere. Of course, this uses that M is connected and that the boundary is actually non-empty. So this shows me that S is 0, so the kernel is 0, and we have proved the first corollary. Good. Okay, that's nice. And here comes the interesting modification of this, which will allow us to actually produce a non-trivial index. And that's a generalization of an old theorem by Daniel Fried, who proved it for the spinorial Dirac operator decades ago. So let's assume that the boundary of the manifold can be decomposed into connected components, n1 up to nk, or the n's actually don't have to be connected, but they can also be collections of connected components. So we have such a decomposition of the boundary into n1 up to nk. And to each of these n's, I associate a sign, which I call epsilon. So n1 gets associated epsilon 1, which is plus or minus 1. So each of them gets a sign, which I just choose in an arbitrary manner. And now I pick my boundary conditions such that these subbundles of the involution come from this Clifford multiplication by the exterior normal vector field, but this time with eigenvalue plus or minus epsilon j. So that means if all the epsilons are equal to 1, then I just obtain what I got in the previous corollary. But I allow myself for some of the components to switch the sign. And in that case, I get an interesting index, namely in that case, the index turns out to be the sum of all these boundary indices where I only have to consider the epsilon j's which are equal to 1. Or you could also do it with the minus ones, and then you would get another sign. And then we can often arrange things in such a manner that I do get a non-trivial index. And we will apply this later when the boundary of the manifold decomposes into two parts. Okay, and once you have the first corollary, then the second one is easy to deduce, because then you just have to check what happens if you switch the sign on one of the components, and then you get to this. So that's not hard then. Okay, so this much about the index theoretical part. Now, before I move to the second part about applications, maybe are there any questions about this? Not right now. Okay, then let me move on to applications to scalar curvature. I want to describe a rigidity result for certain walk product metrics. So what's the setup? I fix a dimension, which should at least be 3. I fix a function, a warping function, which is a positive smooth function defined on some interval. And I assume that this function is strictly logarithmically concave. So the second derivative of the logarithm has to be negative. And now I look at the corresponding warp product metric on the sphere times this interval, where I just rescale the spherical metric by this warping function rho. So that's just a standard warp product metric. And then it's easy to compute the scalar curvature. We have this particular formula where derivatives up to order 2 of rho enter, and we can also compute the mean curvature of the slices for fixed theta, and in particular of the boundary components at theta minus and theta plus, which is essentially then given by the logarithmic derivative of rho at those points. And this sign in front here comes from the fact that I want to always do it with respect to the outer normal. So I have a different direction at theta minus than at theta plus. So then I get this formula. All right. And I'm interested in this kind of walk product metrics. And what are typical examples? So here are some examples. Of course, the spherical case is well known to us, where the warping function is a sine function. Then what you get is the n sphere with the usual metric, and the scalar curvature turns out to be n times n minus 1. We can look at the flat case, where rho of theta is just rho itself. This gives me annular regions in Euclidean space. Of course, scalar curvature is 0 in that case. We can also look at the hyperbolic case, where the warping function is sinh, and then the scalar curvature is minus n times n minus 1. And these three examples all embed into a one-parameter family of metrics known as the Schwarzschild for the flat case, Schwarzschild de Sitter for the spherical case, and Schwarzschild anti-de Sitter for the hyperbolic case, which also can, in principle, be written in such a form. But the warping function will not be very explicit if you do that for those metrics. That's why they are typically written down in a different way. But anyway, so these examples that are listed here will actually give you all warp product metrics of constant scalar curvature. Of course, warp constantness is not assumed here, but so these are important examples anyway. So typical examples to think of. So also note that I'm not making any positivity assumption on scalar curvature here. So it's just this strictly concaveness of the logarithm of rho, which is important. It's not assumed in any way that the scalar curvature is positive. So this hyperbolic case is also very well allowed. All right. And so that's somehow the model spaces. And now let me pick a Riemannian manifold of dimension n, compact spin with boundary as before. I have a map from that manifold to this warp product metric, smooth map, warp product manifold, smooth map. The boundary should be mapped to the boundary of the warp product metric. The map should be topologically non-trivial in the sense that it has non-trivial degree, and it should be one Lipschitz to compare the two metrics. The one on M and the one on the swap product. So that's what I'm assuming. And then we have the first theorem giving us a scalar curvature rigidity for these swap product metrics, namely, if the scalar curvature of M is at least that of the model space, and the mean curvature on the boundary is at least that of the model space on the boundary, then this map must actually be an isometry. So that's the first theorem. And yeah, let me say something about the proof, how this is being done. And I will restrict myself to the case that the manifold is even dimensional, because that's the more interesting case. If n is odd, the proof is simpler, but I would like to show you the extra arguments that you need in order to treat the even dimensional case. Why is even dimensions harder than odd dimensions? Well, we will use this holographic index theorem to make a computation of the index and reduce it to the boundary of the manifold. But if n is even, then the boundary is odd dimensional. And then on an odd dimensional closed manifold, an index is typically 0. So that creates problems. So that's why we cannot directly work with the manifold in that case. And so we increase the dimension of the manifold by 1 by adding an S1 factor and call the resulting manifold M twiddle. And the metric is such that I just take the product metric, but I rescale this S1 metric by a large factor R. Later, I will actually let this R tend to infinity. So think of R as a large factor. So we take the product with a large circle. Okay. And now, this is just notation. So the boundary of M decomposes into two parts, namely the one that maps to theta plus part of the warp product, and the one, so this corresponds to the two ends of the interval in the warp product metric. Remember, the boundary is mapped to the boundary, so we have some part of the boundary which is mapped to the theta plus to one end of the interval, and so the other part is mapped to the other end of the interval. So we have this decomposition. And we have the corresponding decomposition when we just cross everything with S1, which you see here. Good. Okay. And the first lemma that we need is that we find a smooth map from Sn-1 cross S1 to the sphere which has non-zero degree. It has actually a degree plus or minus 1. So the sign just depends on your orientation convention. It's not relevant. And we can also control the pullback of the standard metric on the sphere by this given metric. So if R will be larger than 4, then we actually have an inequality, a Lipschitz map. And so that's something we'll need. And I want to give you the proof by movie. So here's the proof. So on the left side, you see, on the left side here, you see the base thing is Sn minus 1. And the vertical thing is the S1 factor. So think of the thing as identified bottom and top. So this gives you Sn minus 1 times S1. And the right thing is the n sphere. And in the movie, so this red circle will move up this manifold, and you will see the image under the map H on the n spheres to get an idea what the map does. So let's run the movie. So you see the Sn minus 1 sweeps out the n sphere up to halfway, and then the rest, when you go further up, then everything gets collapsed to one point and moves back down to the South Pole. And then the whole thing repeats itself. If you look at that, then you see that certainly this map will have index 1 because a generic point on the target sphere has precisely one pre-image point. And it's also easy to check that this bound on the metric is satisfied. Of course, you can write the formula down explicitly for this map. All right, so that's just an auxiliary map that we will need in order to map everything to the n sphere again in the end. All right, now let's continue. So we have this map M, this manifold M cross S1, which I called M tilde with this corresponding metric, and we have this decomposition of the boundaries. Now I write my map from the manifold to the n minus to this product manifold as phi comma theta, where the phi part maps to Sn minus 1 and the theta part maps to this interval. And from that we can define now a map F tilde from M tilde to the n sphere as follows. We take this phi part, which maps M to the n minus 1 sphere, which is phi, and then the part from S1 is inserted into H so that we end up in the n sphere, right? So H maps Sn minus 1 cross S1 to the n sphere. So that gives me a map F tilde that maps my M tilde twiddle to the n-dimensional sphere. And now I can play the Yarul game in some sense. I want to pull back the positive or negative chirality spinors on the n sphere via this map F twiddle to M twiddle. So yeah, n is even. So the spinor bundle of the n sphere, the spinor bundle of the n sphere decomposes into these chirality subbundles, and I can pull back either E plus or E minus along F tilde to M tilde. And now I have a choice between 4 boundary value problems. I can either pull back E plus 0 or I can pull back E minus 0. And I can, on these 2 parts of the boundary, choose involutions for my boundary condition. And the involution is I times the Clifford multiplication with nu, and I can pick the signs. And I always pick one minus sign on one part and a plus sign on the other part. But I have a choice to where to put the plus part and the plus sign and the minus sign. So I have 2 possibilities for E plus and 2 possibilities for E minus. And now these 2 boundary conditions, this one and that one, for example, they are adjoint to one another. So the indices that I obtain by twisting with these bundles and these boundary conditions, they will be negatives to each other. So the corresponding index of this one will be the negative of the index of that one, because the boundary conditions are self-adjoint to each other, and similarly here. And what I want to get is one boundary value problem out of these 4, which has a positive index. That's what I want, because positive index means I can find a solution. And well, since they are negative to one another, if there is no positive index appearing here, this means that all the indices have to be 0. This is the only thing that could happen, that all the indices are 0. But then we can apply the holographic index theorem and compute these indices by reducing them to the boundary, and then apply the usual Atiyah-Singer index theorem. And then you are basically doing the same thing that you do in the Laruelle theorem. You pull back let's say, positive chirality spinors from the sphere to your manifold, and then you know that the Chern character of that thing is non-trivial. The degree of the pullback map is also non-trivial, so you get a non-trivial index, and you can you see that you can do it, that you get a non-trivial thing. So that's why you can find, out of these 4 potential boundary value problems, you can certainly find one which has a positive index. I'm being a bit short here, but this holographic index theorem allows you to reduce things to a closed case where the arguments are well known, how you can do that. Okay, so let's pick one of the boundary value problems with the positive index, and then we get a solution, certainly, of the corresponding boundary value problem. So we find a smooth spinor field, smooth up to the boundary, such that in either twisted with E plus or twisted with E minus, such that the corresponding boundary conditions are satisfied. Okay, so we have this smooth solution. That's good. And now here we introduce a sort of modified connection on M tilde. So what we do here is the following thing. Look at the vector field T on the circle factor, normalized to have length 1, and then sort of subtract the contributions from this S1 factor and differentiate only in the M direction. So that is the usual standard connection on our spinor bundle, twisted with the pullback bundle. And then we have some extra 0 order term which we add here, where the logarithmic derivatives of our warping function enters. So that's just a smart choice of modified connection, if you like. It's not really a connection because in T direction it does not differentiate. So, but let's make this definition. And then the crucial thing, and that really takes quite some work and quite some computation, is to check that my solution U satisfies such an inequality. So if I apply this operator that I just defined to U and take its L2 norm squared, then this can be estimated by U squared itself divided by the warping function. So that's what we get. And this then uses all the assumptions that we need. You have to do some integration by parts. The boundary terms that appear there will be controlled by the boundary conditions that we have imposed and so forth. So that takes some work to get that. But at the end of the day, this is what you get. And this is an integral over M cross S1. Right? Remember, M tilde is M cross S1. And if these integrals over M cross S1 satisfy this inequality, so if you first integrate over M and then over the circle, at some point it must also be true for a particular value of the circle, some value T0 in the circle. So you get that for this hypersurface in M tilde, which is essentially M. The same thing must be true as well. So that's you get, and let's pick that. So that's what we find. So here again, the same thing. So our solution satisfies this inequality. And now it's important to see that in this prefactor that we have here, the R appears in the denominator. So if R is large, then this prefactor is very small. So that's why we now make a procedure, limit procedure, and send R to infinity and pick a U for each of these R's and pass to a limit. Then we will end up with a spinor on the manifold for which this right-hand side is actually 0 because this prefactor tends to 0. So then we find a non-trivial spinor field on our manifold M, satisfying the corresponding equation here, where the equation, the P tilde, now reduces to the equation that you see down here. So that's now really a modified connection on our twisted spinor bundle. And what we have found is a parallel spinor field with parallel with respect to this modified connection. And if you have such a thing, this always imposes very strong restrictions on the geometry of the underlying manifold. Okay, so here again, so we have this solution to this overdetermined equation. And now, if you look at the corresponding function, so remember there was this function f tilde, which we used to pull back our spinor bundle from the sphere to m tilde. If you insert this value of the circle factor, you get a map from the manifold M to Sn. And it turns out that the differential of this manifold now has these singular values. So there's one direction which corresponded to the circle direction, where the singular value is 0, but all the other singular values turn out to be 1 on rho of theta. And this you can always get an estimate of the singular values in one direction, but if you have this particular kind of spinor field, you will see that these estimates are actually equalities, and that's why you can determine these singular values precisely. Right? So if you have this, for example, then you also have an explicit formula for the curvature tensor applied to S, and this can be inserted into the Weizenberg formula, and this is why you will get very explicit formulas for everything then, if you have this equation. Anyway, so you have determined the singular values of this function f from m to the n sphere. And from that, it's easy to deduce that your metric must actually be of this form. And that, in other words, you have proved that your map phi is a local isometry. Since the domain is connected and the target is simply connected, it's actually a global isometry. And that concludes the proof in the even dimensions. And in odd dimensions, it's easier because in odd dimensions, you don't even have to take the circle factor. At this circle factor, you can work on the manifold directly. And you don't need this limit procedure. Okay, good. So that's the first result, the first application to scalar curvature geometry. And the other one, and that will be the last result I want to explain, is a Yarul type theorem for incomplete metrics. So again, we are in dimension 3 at least. Now we look at a non-compact manifold. So in this case, it's just the sine function. So we are looking at a part of the sphere here. So this is the sphere with the north and the south pole removed, written as a walk product metric. So in that sense, it's a very special case of the previous situation because only the sine function is allowed. But we are no longer in the compact case, because we have an open interval here. So it's just the standard sphere with north and south pole removed. And what our manifold previously gets now replaced by manifold omega, which is non-compact, connected n-dimensional spin manifold, but without boundary. So it's an open manifold. And we assume that we have a Riemannian metric on omega, which generally is incomplete. Again, we assume that the scalar curvature of this omega is bounded by the scalar curvature of the model space, which is n times n minus 1, and that we have a smooth map. And now theorem B tells me that if this smooth map is proper, has non-zero degree, and is one Lipschitz, similarly to the previous situation, then it must be a Riemannian isometry. And for example, you could apply this to the manifold omega being the punctured sphere itself, with just replacing the standard metric G0 by some other incomplete metric on the sphere with the antipodal points removed, such that the scalar curvature is bounded by the standard curvature, and such that the metric itself is bounded by the standard metric, so that the identity becomes one Lipschitz. So we could apply this to the identity map. And then this would give us exactly Yarul's theorem, but not for compact manifolds, instead for the sphere with two antipodal points removed. So that would be one particular example here. And the motivation for studying this goes back to a question asked by Misha in his 4 lectures, I believe, namely for which closed subsets of the sphere sigma is the complement Sn minus this subset still scalar curvature rigid in the sense of Yarul's theorem. And our theorem says it's true if sigma is a pair of antipodal points in all dimensions, at least 3. And Misha sketched the proof using mu bubbles, so a different approach for antipodal points. And that was worked out in detail by Julio Xi in dimension 3. You also using mu bubbles, and an alternative proof was also given by Hirsch, Casares, Curie, and Zhang, also in dimension 3. And so we do it with Dirac operator methods in all dimensions, at least 3. Okay, and you might ask, what about the case of dimension 2? I've always assumed that the manifold is at least 3-dimensional that we are looking at. And in fact, in 2 dimensions, theorems A and B do not hold. And there's a very simple counterexample, namely pick some constant larger than 1. And now on S1 times the interval 0 pi, look at 2 metrics. One is the standard metric of the punctured sphere. And the other one is the same thing, except that you add this additional factor lambda in front of the sign factor. And the map that I'm taking is just the identity map. And then you can compute that the scalar curvatures coincide for both metrics. So lambda does not play a role here. And the mean curvatures also coincide. And phi is 1 Lipschitz because lambda is larger than 1. But it's not an isometry because lambda is strictly larger than 1. And so that's a counterexample to the corresponding statement in dimension 2. That's why we had to assume that dimension is at least 2 in both of the theorems. Now, as far as the proof is concerned of this theorem B, so since my time is up, I can just say it in a few words. So what you do is this. So you will have this sphere with 2 points removed. So you remove small open disks around this point. Then you will get a manifold with boundary. And you remove from omega, you remove the corresponding pre-images. Then you are in the situation that we were before, that you have manifolds with boundary. And you map to some warp product like that. But the problem is we cannot apply theorem A directly because theorem A requires a bound on the scalar curvature, which we do have, but also on the mean curvature of the boundary. And if we remove something from omega, we have no idea what the mean curvature of the corresponding boundary will be. So there's no control on that whatsoever. And this is where we borrow ideas from papers from Cecchini and Zeidler, where we just add a suitable potential which grows fast enough to dominate each mean curvature that you might possibly have on the boundary that you produced on omega. So you can add a very brutal potential which will dominate everything anyway, and then do a similar computation as they do, and then a modification of the methods of the proof of theorem A will give you this result. Yeah, that's very vague, I admit, but for reasons of time, maybe I cannot say much more than that here. I should also mention that, funnily enough, 1 day after our paper appeared on the archive, another paper by Wang Xi appeared, which has a lot of overlap with our paper concerning the results. The methods might be somewhat different. I didn't have the time to check. So many of these things are also discussed in their paper. And it's very interesting because they also treat the situation where you map not to a sphere, but to a torus. So you look at what products of a torus. And I should mention that. So this was 1 day after our paper. Okay, and I think that's what I wanted to say, and I thank you for your attention.